with Rayleigh scattering. As we all know that Rayleigh scattering is by bound electrons, and it was first it has been named after Lord Rayleigh, and Rayleigh was the person who studied the scattering by gases. And you must already have read in optics about Rayleigh shift. By the change of the refractive index of the gas, there is a shift in the interference pattern, and that is called Rayleigh shift. So he was the person who was studying scattering of gases, and this scattering has been named after Lord Rayleigh, whose original name was John Rayleigh, and he was given the title of Lord. So basically, it is an elastic scattering of particles which are much smaller than the wavelength of the radiation. This is the basic criteria. And the for the light with frequencies well below the resonant frequencies of the scattering particle. What we mean by the resonant frequency of the scattering particle is the natural frequency of the electron. We will see in detail while we will discuss the theory, but it is the natural frequency of the electron, and the amount of scattering is proportional to 1 by 4th power, like it is 1 by lambda to the power 4. So it's inversely proportional to the 4th power of the wavelength. We will be analyzing it in theory. The oscillating electric field of the light acts on the charges within the particle, and the particle becomes a small radiating dipole. These particles may be individual atoms or molecules, or it may be electrons only, bounded inside the atom. And this scattering is responsible for the scattering of sunlight in the Earth's atmosphere, due to which we see the blue sky and the reddish sky in the evening. And these are the three effects: the blue sky, the red sunset, and the color of the moon's sky. So just see here. As the wavelength increases, the scattering also increases exponentially. So the red light is scattered the least, and the blue light is scattered the most. And due to this, since the blue light is scattered the most, so the sky appears blue. And the scattering efficiency, like I said, that the scattering is proportional to the inversely proportional to the 4th power of wavelength. So it will be directly proportional to the 4th power of the frequency. So higher the frequency, the stronger is the scattering. Similarly, you can see, and this scattering is primarily due to the polarization in the molecules. So if I take a polarized light, a camera with the polarizer, this is without a polarizer and this is with the polarizer. You can see the difference in the sky color. The place and everything is the same. The clouds are also the same. Only the polarizer has made the difference. The blue color has increased. So this kind of scattering increases with the polarization of light. This is the redness in the sun at the time of sunset. This is also due to Rayleigh scattering. So this was an introduction. Now let us move to the theory behind this. Scattering by bound electrons. So when an electron system is acted upon by an electromagnetic radiation, and this is monochromatic radiation, then the vibrations are of the type of forced vibrations, because firstly the electron will vibrate with its natural frequency, and on this natural frequency the forced oscillations are superposed, and ultimately the continuous vibrations with frequency of the force. Now, to develop the theory, we should see what are the forces that are acting upon. So, the first one is the Newtonian force. Mass into acceleration. The second is the self force of electron, which is directly proportional to the instantaneous velocity of electron. This instantaneous velocity is dx by dt. Third force is the restoring force. The fourth is the forced by the electromagnetic radiation, and if the electromagnetic radiation is the motion is in x direction, this is the electric field, and multiplied by the electron charge. So these are the four forces, and now we proceed to write the equation of the force. That is the equation of motion. Alpha is the damping constant. I will multiply or divide this equation by m. I called this quantity as gamma. It's a simple substitution. Gamma has nothing to do with the relativistic factor gamma. And this where omega 0 is the natural frequency of oscillation. Now this is my current differential equation. I name it as equation 1. Its solution will consist of two parts, as we all know. First one will be the complementary function, second one will be the particular integral. So let's start with complementary function. We will take the left hand side. We will have an assumed solution. This alpha and the previous alpha is different. Substituting this x into this equation, this is the quadratic equation. Note value. So now I will substitute this alpha back into this x. Mhm. We will separate these terms. This I can name as equation 2. Now we will calculate the particular integral. Let's take the equation of motion once again. Let the solution be so this substitution will give me from this substituting this b into this equation. So now we have calculated the complementary function and the particular integral both. So we will just proceed with this particular integral. Right now we will not write the total solution, but we will simplify this particular integral. So in complex quantity, in the case of complex quantity, this is a complex quantity in the denominator. So first thing what we would like to do is to make this denominator a real quantity. So what we should do? We should multiply and divide it by the complex conjugate of this. We will separate this denominator. Half of the power here and half we will take it inside. I am separating the real and imaginary parts of the numerator. Okay, where this term positive and this is sorry. So this will give me e to the power I del. I will combine both the exponentials. So this is the final particular entry. So now this is the PI. We have already calculated the complementary function. So the general solution x is equal to PI. Now consider the CF portion, this portion. This is the damping term, and this due to this damping term, the oscillations will be damped and will ultimately die out. So the dominant solution will be only this term that will prevail in the forced oscillations that will be continuous, because these will die out and the second one will remain for the time, so the scattering may take place. This will die out before the scattering can take place. So there is no point in taking these terms. Only this term we will take into account. So the resultant displacement is this was the displacement that we arrived at yesterday. Now we see that the oscillating charge, this is the exponential term is the oscillating term. That means this displacement is oscillatory in nature. So the charge is oscillating. So the oscillating charge is equivalent to an induced dipole and this dipole moment is given as E into X. Now we will take the oscillatory and the constant parts separately. These are the constant terms and this is the oscillatory term. So I have taken the oscillatory term as such, and the constant term I have assumed it as an amplitude, constant amplitude P0, whose value is this is the amplitude of the dipole moment. Now this oscillating dipole. So this dipole will be oscillatory in nature because we have an oscillatory term there. So this oscillating dipole will radiate energy and the average energy radiated per second per unit area is denoted as W with the subscript scatter. From the knowledge of the oscillating dielectric dipoles, we have this expression. We will be discussing this oscillating electric dipole separately after finishing the scattering. This formula I borrowed it from there. I'm substituting the value of P0 square here. This is these terms, and now we substitute P0 square. And this. Now the intensity of incident radiation is given by this expression. This is equation 6. So now the differential scattering cross section is given like this. We have got both the values of W scattered and P incident from the equations 6 and 7 just now. Now we will substitute them. rearranging the terms and combining the like drones. You have studied already that this is classical electron radius, where we have used the relation omega 0 and gamma are the properties of the scatterer. So we can say that the scattering depends on nature of scatterer through omega 0 and gamma. The scattering depends on the angle of scattering. The angle of the scattering is theta. And thirdly, scattering depends on the incident radiation through omega. Omega is the frequency of the incident radiation. So we have the differential scattering cross section. And after differential scattering cross section, like the previous one, we will proceed to obtain the total scattering cross section. The integration will be the same as we did in Thomson scattering. This is the total scattering cross section. We will analyze some cases. We will consider the difference term in the denominator. Consider a situation where omega is much greater than omega 0 and gamma is very small. In that case, this will be reduced to this. This is the expression for the Thomson scattering, and under these conditions, the charge behaves as free charge. If the reverse, omega 0 is much greater, this is the proper Rayleigh scattering. And just notice one more thing. It is directly proportional to the fourth power of the frequency. That means it is inversely proportional to the fourth power of the wavelength. This is very important. Third condition is omega is equal to omega 0. Then this is called resonant scattering. So resonant scattering is a scattering at resonance by a bound atom, and under these conditions sigma t is maximum. The total cross section is maximum. This type of scattering is, you can, as an example, you can take, if we have a sodium vapor and we illuminate it with another sodium light, both the wavelengths will be same, the frequency will be same. So this kind of scattering will take place. When two sources of the same frequency are acted upon by one another. Now, as I pointed earlier, here this is the case. So we see that greater is the wavelength, the lesser is the scattering. That means for shorter wavelength, more scattering. So the blue light scatters most, and that is why the sky is blue. Longest wavelength, least scattering. That is why red colors is scattered least, and so the danger signals are red. Sun set or sunrise, you see the redness in the sky. At resonance, we have the resonance scattering. Below it is the Rayleigh scattering, and if the value is above the resonant frequency, then it is the Thomson scattering. So this is how the Rayleigh and Thomson scattering can be analyzed as a specific case of the Rayleigh scattering. From our expression, we see that we can take the Thomson scattering as a special case of the Rayleigh scattering. So this ends our Rayleigh scattering. We have calculated the total cross section and the differential scattering cross section, and we have also seen some of the special cases.